Hello everyone, I'm Zhu Ping, coming from Zhejiang University. Today, I'd like to share a recent study, Attention Without Working Memory, a future-specific working memory gate for attended information. Each time we open our eyes, we are surrounded by an overwhelming amount of information. However, our working memory can hold an extremely limited amount of information at any given time. That is, 3 to 4 items. So, obviously, our working memory must select the most relevant information for further processing, and attention has commonly been believed as a gatekeeper of working memory, which determines what information will be selected into working memory. This assumption has received many supporting evidence from past research. On the one hand, both behavioral and neuroscientific studies demonstrated that attention could enhance working memory. On the other hand, some studies showed that without attention, participants could even fail to consciously perceive the very salient stimuli, as shown by the classic inattentional blindness and change blindness. However, in most previous studies supporting the obligatory role of attention in opening working memory gate, the attended information was often also the one needing to be remembered. In present study, we created a novel design wherein the requirement to attend to and the requirement to memorize was separated to reinvestigate the role of attention in working memory. For example, in the experiment, we asked the participants to find the colored target square among black distracted squares and report its location at the end. In this case, color is the information needed to be attended to and used to perform a task, but not need to be remembered or reported. This kind of information was termed as a key feature. In section 1 of our study, we sought to examine whether the fully attended key feature has ever been encoded into working memory, based on 3 different characteristics of working memory. Experiment 1 explored whether the key feature could produce the working memory-driven attentional bias effect. Participants were asked to find the colored square and report its location. Here, the color served as a key feature. During the maintenance, there was a search display where participants needed to find the target diamond and report the line orientation inside it. In the key-related condition, the color of one distracted circle matched the key color. In the unrelated condition, one distracted circle was filled with a new color. According to previous studies, if the key color was selected into working memory, the distracted circle containing the key color would automatically attract attention and lead to longer search time in key-related condition compared with unrelated condition. The ISI between the memory display and the search display could be 0, 100, or 700 milliseconds. The results showed no significant difference in search time between key-related condition and unrelated condition in all ISI conditions. In other words, the key color could not produce a significant working memory-driven attentional bias effect. Experiment 2 explored whether the key feature consumed working memory capacity. This was a dual-task design, including a color change detection task and a visual search task like Experiment 1. Participants were divided into 2 groups. For the key group, the letter color served as a key feature. For the working memory group, the letter color served as a response feature. The results showed that Compared with response feature, the key feature consumed much less working memory capacity. Notably, the significant difference found in the key group was very likely caused by a dual-task interference, rather than that the key feature was encoded into working memory. Experiment 3 adopted CDA to online track the memory trace of the key feature. In the pre-surprise trials, participants were instructed to report the location of the target polygon, making its shape a key feature. In the post-surprise trials, participants were required to report the shape of the target polygon, making it a response feature. The results showed that the CDA was only found when the shape served as a response feature, but not when it served as a key feature, suggesting that the key feature has not ever been selected into working memory. Overall, Section 1 provided convergent evidence that the attended key feature has not ever been selected into working memory, suggesting that there exists a working memory reselection process for attended information. In Section 2, we sought to further investigate how does the working memory gate operate to achieve such a reselection. In Experiment 4, we tested whether the key color could still be blocked out of working memory when participants were asked to simultaneously memorize another color. This experiment was very similar as Experiment 1, except that participants were additionally required to remember and report the color of the fixation cross in Experiment 4A. This fixation color task was probed after the location task. Experiment 4B was conducted as a control, and it was identical to Experiment 4A except that participants were asked to ignore the fixation color. The results showed that the key color produced a significant working memory-driven attentional bias effect in Experiment 4A, but not in 4B, suggesting it was selected into working memory when another color was memorized simultaneously. Experiment 5 adopted the irrelevant changing distracting effect to probe the working memory representation of key color. Here, participants were required to find the colored target and remember its shape, wherein the color still served as a key feature. In later shape change detection task, the color could be changed or not changed. In Experiment 5A, participants needed to simultaneously remember and report the color of the fixation cross, while in Experiment 5B, they just ignored the fixation cross. The results showed that the key color produced a significant irrelevant change distracting effect in Experiment 5A, but not in 5B, replicating and extending the results of Experiment 4. Experiment 6 examined whether the working memory reselection of key color would happen while participants simultaneously memorize a shape rather than a color. In this case, participants needed to memorize the shape of the central stimulus. The results showed that the key color could not produce the working memory-driven attentional bias effect, indicating the key color was still blocked out of working memory when another shape was memorized simultaneously. Experiment 7 examined whether the working memory reselection of key shape would happen while participants simultaneously memorized another shape. The memory representation of the key shape was probed by the irrelevant change distracting effect. In Experiment 7A, Participants needed to simultaneously remember and report the shape of the central stimulus, while in experiment 7b, they just ignored the central shape. The results showed that key shape produced a significant irrelevant change distracting effect in experiment 7a, but not in 7b, again replicating experiments 4 and 5, but using shape instead of color. Overall, Section 2 demonstrated that the working memory reselection process operated in a feature-specific manner. Basing on these results, we proposed a working memory reselection model. There exists a specific working memory gate for each virtual dimension, for example, the color gate, the shape gate, and the reselection could occur between different feature gates, but not within the gate. For example, our brain could selectively open the color gate while close the shape gate at one time, even though both color and shape were fully attended. However, once the color gate is open, all attended colors would be selected into working memory. The current study is supported by this fund, and thanks to my advisors and colleagues in our lab. Here is also an advertisement. Postdoctoral candidates are very welcome in our lab. Please contact Professor Chen if you have any interest. That's all. Thanks for listening.